Graphing is one of the most important skills and abilities that you can learn for dealing with science, engineering, and really any aspect of nearly all fields. Graphs can be done either by hand or many times now on graphing programs. If you were to graph something by hand, it must be done on graph paper, so that way those looking at the graph can see what the actual values are. Other times you can graph using a number of different programs. Your calculators can graph, your phones have graphing apps, and you can graph in a lot of different computer programs like Excel, Maple, Origin, MATLAB. There are a lot of different ways you can graph. And interpreting those graphs is something that will help you throughout this course, science, engineering, and a lot of aspects as your future careers.
This first experiment focuses on graphs and the importance of graphs. Throughout the experiment, you will be determining slope and intercept from data points as well as different graphs, and preparing your own graphs. Graphs are something that are very important, not only in chemistry, but in almost every other topic, from history, business, all science, engineering, the medical field. Knowing how to create and interpret different graphs is useful, if not required, for a number of these different fields. Graphs are used to display a large amount of information in a quick way. In place of a large table with a lot of numbers, a graph can be used to see what is the overall trend of those numbers over time or over the course of the material. Does the number increase? Does it decrease? You wouldn't necessarily know that instantly from a big table of numbers, but from a graph, you can see that quickly. There are a lot of different types of graphs, from bar graphs or histograms, line graphs, pie charts. But in this course, we will be using what's referred to as a scatter plot. This is where both the X horizontal axis and the Y vertical axis vary with each other. So it's not a set 1, 2, 3, 4, 5 going across the bottom. It's whatever the data points happen to be. A lot of the graphs in the course are going to be linear graphs. That is, they're going to give straight lines. And a straight line has the equation form of y equals mx plus b, where y is the value along the y-axis, that vertical axis, up and down. X is the value of the data point along the horizontal axis, left to right. M is the slope of the graph, which is the rate of change. How much does the y value change if you move the x value? That's what the slope indicates. And B is the y-intercept. Where does the line, where does this graph cross the y-axis? This would be the same point where x is equal to 0. If you set x equal to 0, that whole term cancels out, so you're left with the equation of y equals the intercept value. Throughout the experiment and throughout the course, you're going to be calculating slope and intercept for these straight lines. Calculating slope can be done very easily through graphing programs or even calculators, things like that, but it is good to know what the slope actually is. And if you have just a couple of data points without a graph, you can figure out what the slope of that linear straight line is. So as I just mentioned, the slope is the rate of change at which the y values change with respect to the x values. A slope of 1 would mean that every time x increases by 1, y also increases by 1. Calculating the slope is termed the change in y over the change in x. Between two different points, the difference between the y values, divide it by the difference between the x values. Any 2 points can be used to make a straight line. You can think about if you have 2 points, if you have 2 objects anywhere, you can draw a straight line between them. And you can calculate a slope from that. So yeah, looking at the slope, you have the change in y over change in x, or the second y value minus the first y value over the second x value minus the first x value. A lot of times this can also be referred to as final minus initial. Where is your starting data point? Where is your ending data point? So now that I've talked a little bit about graphs, I'm finally showing you one. Here is a graph of a straight linear line. You have the x-axis going left to right, and the y-axis going up and down, vertical, with this straight line. On this straight line, there are 2 specific data points that I highlighted. In this point, you have 7 and 4.375. When you're given a set of data points like this, the x value is first and the y value is second. That means for this particular point, the x value is 7 and the y value is 4.375. There's also a second data point listed down below, which is -5 for the x value and -3.125 for the y value. Looking at the change in y, the change in height, you have one data point minus the second data point. So 4.375 minus -3.125. That is a difference of a value of 7.5. It is 7.5 units from this point all the way up to this line right here. The same can be done with the x value, where you have 7 minus -5, and that's a difference of 12, meaning from this data point to this data point, it is 12 units wide. Overall, the slope is change in y over change in x. The rise, the height, over the run, the length. So therefore, the slope of this particular line in this example is 0.625. This slope is constant throughout the entire line. Any 2 points you pick on the line itself will give you a slope of 0.625. The next portion of the straight line is the intercept value. And this is where the graph or where the line intersects the y-axis. In this previous slide, I made sure the point crosses through 0. The intercept is 0. It crossed right at the 0 mark. But when you're not every graph will cross the y-axis at the 0 mark. It will have a slope associated with that. And to calculate that just from the numbers, just from the data point, all you need is a single data point, one xy value, and you should have the slope as well. So now in this case, I have a graph with the same slope. So notice the intercept changed, but the slope did not. By changing the intercept, you are just moving the graph up and down somewhere. If you change the slope, you'll be changing the pitch or the rotation of this line. But by changing the intercept, all you're doing is moving the line up and down. So if I have this line, now I have two different data points. If you go through the slope calculation, these two data points will give you the same exact slope, 0.625. But I can pick one of these data points, a point that's exactly on the line itself. And if I know the slope, I can solve for what the intercept is. The equation for a straight line is y equals mx plus b. So if I know the slope, that m value, and I have, well, at this data point, the x value is 7, and the y value is 7.375. These are the data points. So you can plug in the x value for x, the y value for y, and since you have the slope, you can run through this calculation to figure out what is the intercept for this particular line. When you have a set of data on your own and you need to prepare a graph from it, you first need to figure out which set of data, which column of numbers would be going on the x-axis, the horizontal axis, or the y-axis, the vertical axis. And typically in a lab setting, like a chemistry lab, the x-axis would be the value that you control, that you are physically changing. That is the independent variable. If you're changing the thermostat from one setting to another, that's what you're controlling. And whatever happens because of that, the temperature goes up, that would be on the y-axis. So in the case of something like concentrations and volume, you're choosing, let's say, the size of the container. You're choosing that. So as you change the size of the container, what would be dependent on that? So once you have figured out what you should put on the x-axis and what you should put on the y-axis, you should look at the scaling. So if your data only goes from 1 to 10, you should not make a giant graph that goes all the way out to 100. There will be a lot of empty space on that graph then, and you really don't need that. Either if you were to graph by hand or if you were doing a graph through a graphing program. The other thing would be to make sure the scales or the values on the numbers are evenly placed. So the graph itself, the axes numbers should be evenly spaced. So on this graph here, I go from 0, 5, and 10, and each of the markings in between then would be one unit. You would not put a graph that lists, let's say for the y-axis, negative 0.125, then 2, then 5, then 7.375. That's all over the map. You want to make sure the axis values, the scale, is evenly spaced. When you're graphing something, again, either if this is either by hand or through a graphing program, you want to make sure that it is appropriately labeled. In the previous graphs that I showed, if these were to be handed in, they would not get very good scores. They're not labeled with anything. There are numbers. These graphs, while I use them to show how to calculate slope and intercept, are literally pointless for anything else. You want to make sure a graph conveys the information that you want the viewer to see. So because of that, you want to include some sort of a title. What is this a graph of? In this case, I have the sample graph, a calibration curve of crocine scarlet dye at 480 nanometers. I gave a lot of information, but in a very short, precise title. This happens to be a calibration graph. I have the chemical name listed, and I have this constant value, which is the wavelength of light used for this. So if you're given something that's held constant, especially something that can change, if you're given that, that should be included in the title. So if you're given something where it says the temperature of all of this data is 50 degrees, and then it gives you a bunch of data, in the title you should list that the data being shown in the graph was at a constant 50 degrees. So you want to make sure that any of those sort of constant values for the data set are included in the title. Then you want to make sure that the axes themselves are also have a title. So what is the title, or what is the x-axis? What are these values? What is the y-axis? What are these values? In this case, I'm graphing concentration versus absorbance, which is a measurement of how much light a chemical will block. And very important, include the units. In this particular example, I have the units of concentration as ppm, parts per million. But concentration can also be listed in percent, molarity, parts per billion. There are a lot of different units that can measure and mean a concentration. So when you're graphing something, you need to make sure that the units of these values are also indicated in the title. So a viewer would know that, oh, this is going up to 40 parts per million, not 40%. When you're doing a graph, especially for in this course where you're only going to have a limited number of data points, you want to make sure to include all of these separate data points, so that way the viewer or the person looking at the graph can see the exact measured values throughout the entire data set. And last, you want to make sure that it has a trend line. This is the line of best fit that goes through the data. So it doesn't have to fall, or all of the data points don't have to be exactly on the line. This is an approximation of overall what does the data show. Other things that you can also include on a graph, they're not necessarily mandatory, but can be nice depending on the circumstance, would be grid lines like these. Some professors like them, some professors don't, so get a sense for that. But in general, they're not necessarily good or bad. It's just a way for the viewer to get a better approximation if they were using the graph directly. If you have multiple lines graphed on the same graph, you want to include some sort of a legend or table to say which line is what. Especially for linear graphs like this, it might be useful to include the equation of the line as well as the r² value. This would be much more useful in upper level courses. Chemistry would be physical chemistry or analytical chemistry, but also a lot of engineering courses or physics courses, because the r² value is a measurement of how precisely this line, this equation, fits with your data set. So one more thing about trend lines. When you're looking at trend lines, like I said, the data points do not have to fall exactly on the line. They can be, the line itself is the line of best fit, the trend for the data. But because of that, if you're going to be calculating slope or slope and intercept of a data set, you need to choose values that are on the trend line itself, not necessarily individual data points. So this black line is the overall trend, the overall line of best fit for this data. So to find the equation of the line, the slope, and the intercept for these values, you would choose 2 points on the line itself. However, if I chose, let's say, this data point here and up here, the straight line between them is very different than the trend of the entire data set. Same thing with these 2 points over here, these last two. If I'm looking just at these 2 data points, there is a much different slope and intercept between them, and that does not represent the whole data set as a whole. So especially for if you're graphing by hand, you should always make sure to calculate the slope and intercept using points that actually fall on the line. In the virtual experiment, it is separated into 3 different parts. The first part looks at calculating slope and intercept for different lines. The second part is dealing with graphing of temperature scales, and the third part deals with logarithmic functions and nonlinear graphs. The first part looks at calculating slope and intercept and utilizes a PhET simulation, which is found at this link. Initially, you will be given a few different setups of different line points, of which you will determine what is the slope and intercept based on the numerical x and y values. Second, you will go to the following PhET simulation and work through the line game activity. You will work through level 6 of the activity, and at the very end, take a screenshot of your final screen. Attaching that to the report please make sure to include the score at the top in your screenshot, as that will be a portion of your final report grade. In Part A, you are using the PhET simulation on graphing lines. You're going to choose the line game option. While you can work through the different levels, we're going to be collecting level 6. When you access level 6, you will see a function and a graph. You will use the colored dots to move the line and graph the function. And then you can check your answer. You will go through all 6 of the different equations and graph each of them, checking along the way. On your final graph, please be sure to take a screenshot of the entire screen, including the total score, your correctly graphed equation, and the equation. In Part A, you will be recording each of the 6 equations used and then uploading a final screenshot at the end. The boiling point of water occurs at a constant 100 degrees Celsius. The thermometer reading, however, does not read exactly 100 degrees. The current thermometer reads close to 99.5 degrees Celsius as the boiling temperature of water. In Part B of the experiment, you're looking at the comparison of different temperature scales. In particular, you're comparing the Fahrenheit temperature scale with the Celsius temperature scale, and looking to see what is the relationship between these two temperature scales. You're going to make or determine the equation of the line that it relates these two temperature scales. And you're doing that by graphing 3 points. These are 3 known points in each of the different temperature scales, Fahrenheit and Celsius. So you're graphing the freezing point of water, body temperature, and the boiling point of water, with Fahrenheit listed on the y-axis and Celsius plotted on the x-axis. And what you can do is, once those are graphed, determine what is the slope and what is the intercept for these two temperatures, how they relate to each other, and determine at what point is the temperature the same. What is the temperature that's the same numerical value in both Fahrenheit and Celsius? The second graph that you're doing in Part B is looking at thermometer calibration. So when looking at a thermometer, it is not always exact. These are manufactured devices, either glass thermometers or digital thermometers, that need to be adjusted from time to time, or at least compared to tried and true 100% physical temperatures. And in this case, you're going to be preparing a calibration graph based on measured known values that are given in in the unknown file. So the unknown files are found on the course Blackboard site. You're going to choose one and record what your unknown number is. So the unknowns will look something like this. The individual files have, for part B, have the measured value of the freezing point of water, boiling point of hexane, and the boiling point of water. So from these three, these are the temperatures that were measured using a thermometer in lab, but these are not the correct temperatures. So the correct freezing point of water is 0 degrees Celsius. The correct boiling point of water is 100 degrees Celsius. But in this case, the measured freezing point was 2.18, and the measured boiling point was 97.18. So what you'll be doing is preparing a graph where these three measured values, freezing point of water, boiling point of hexane, and boiling point of water, are listed, or I'm sorry, are graphed on the x-axis, where the correct true values are graphed on the y-axis. And that should give you a straight line, which you will calculate the slope and the intercept for. You're determining the equation of the line. What is the calibration? What is the correction factor for this particular thermometer? And then you're going to be using that to determine the identity of an unknown solvent. So this last line, boiling point of unknown solvent, this is using the thermometer that gives these values. You put the thermometer in a boiling liquid and it is 80.55 degrees in this example. And what you'll need to do is use the equation that you developed from the line to determine what is the correct value that this is supposed to be, convert that to Fahrenheit, and figure out what is the identity of this boiling solvent. So when you go through that, you're first determining what is the calibration plot, what is the equation that relates the measured value versus the correct value. Once you have that equation, you have a measured value for a boiling solvent. You're going to use the equation to determine the correct value of the boiling solvent, and then compare that value to this list. The identity, the name of the solvent is one of these. All of them are possible, all of them are listed, are contained in the various unknowns. So you're trying to determine what is the identity of your solvent listed in that unknown based on the temperature readings that the theoretical thermometer in your unknown gives you.
Absorbance and transmittance are two properties that are related to how light interacts with solutions. These two properties are logarithmically related. These solutions have different concentrations. The transmittance, or the light that's able to pass through these solutions, is linearly related, and this is typically what's measured in instruments. The absorbance, however, or the amount of light that is blocked by these three samples, is logarithmically related to the concentration. In this part of the experiment, you're graphing how these two properties relate to one another.
The last part of the experiment looks at graphing and interpreting graphs of nonlinear equations or nonlinear lines. These are lines that have a curve, or a graph that would have a curve to it. So it's not exactly straight. And The data that you're given in the lab report deals with concentration and transmittance and absorbance. So this is something that would be focused on a little bit later on in the course or even in Chem 2, but introducing you to the concept that when light is shining through a chemical, through a solution, some of it is going to be blocked by that chemical, and the rest is going to pass through to the other side for you to be able to see. That is the basis of transmittance and absorbance. There is some amount of light that is transmitted through to the other side, and some amount of light that is blocked by the chemical. So the relationship between these two, these two properties, transmittance and absorbance, is not linear. They are logarithmically related. So what you're going to be doing is first preparing a graph from the report form of concentration on the x-axis and the given values of transmittance on the y-axis. Then you are going to convert the transmittance value into absorbance, and that is done through this equation right here. Again, these are not linearly related, they are logarithmically related. And when you can see that when you graph the first graph and the second graph in part C. So to convert transmittance into absorbance, it is 2 minus the log of the percent transmittant value. And you do not need to convert that into decimal. So if a transmittance value is 57%, the absorbance value will be 2 minus the log of 57. And absorbance will be a fraction. Once you have those graphs prepared, in particularly the second graph plotting concentration versus absorbance will be linear. And that way you can determine the slope and intercept for that graph. And when you have that, you're going to go back to your unknown and see that I'm giving you a concentration of copper sulfate. And from that, you're going to determine, using your graph and using the equation from your graph, what is the absorbance value if you're given a concentration of 38 millimolar, and then converting that into transmittance. Likewise, the second value listed is a percent transmission of copper sulfate, in this case 44%. Using your graph and using the equation from your graph, you will need to convert this into absorbance, and then using the graph, determine what is the concentration of copper sulfate that would give this value, this transmission value. So you're going through and calculating two different parts of this unknown. You're given a concentration and asked to determine what is the percent transmittance. Next, you're given a percent transmittance and asked to determine what is the concentration. Those two values are not related. So in your unknown sample, you're given both of those, and you're going to use these equations to determine, given concentration, what is the transmittance? Given the transmittance, what is the concentration? And you're doing this all based on the equations developed from graphs.
overall, you're going to be preparing 4 different graphs. 2 graphs that relate to temperature, and 2 graphs that relate to the property of absorbance and use logs to convert between the 2. As you go through this experiment, as you look and see what these graphs actually mean, I don't like that. As you go through this experiment, you're preparing 4 different graphs. 2 of them are related to temperature, and 2 of them are related to light and absorbance, which is your nonlinear graph, looking at logs and how those relate. As you're going through and looking at these graphs, pay attention to things like units, significant figures, and overall presentation, making sure everything is properly labeled and that you and anyone would be able to interpret what these graphs actually mean.